Okay, so I want to talk about the response of the chemical equilibrium, or I guess equilibrium constant. When you change the pressure and the temperature, how are you going to change the equilibrium constant? And here's an example of what we actually calculated before based on the heat of the delta G of formation for NH3 gas. And this is how we make the ammonia for use in making a lot of different kinds of chemicals. And look at this number. The K value is pretty big. And the K is essentially product, which is ammonia concentration divided by reactants. And the details of equations has been discussed. But the idea is you have a lot more product favor over this at 298. But there is a problem. What is the problem is there is a problem on this. If you ever do this, mix the nitrogen and hydrogen at room temperature. This is a room temperature, right? Nothing happens because of what is called, this is what it's going to actually discuss in chapter 17. As a reaction goes, there's an activation energy. You have to overcome to change A to B. And this activation energy is so high that you need to develop certain catalyst to go there. Okay? So it's all about the Gibbs free energy difference between this and that. And that's essentially what delta G difference is. And that's how the K is being defined. But they don't care about what kind of a barrier do you want to go. So let's say I'm in this place. I know if I go to the 100 miles to the south, there's a very nice, I guess, a paradise there. Okay, but if I don't know, you have to climb the Mountain Everest to go to the paradise. I will never know, and I will be probably happy where I am. I will not change. I will not make a move to the paradise, although because of this is my motivation. So there's a lot of motivation for this mixing nitrogen and hydrogen thermodynamically in terms of equilibrium perspective. They are really in favor 1,000,000 to 1 to the ammonia. In reality, you don't get this one. So then what people do is, okay, so you need to, I guess, activate this one. So you need to give a temperature going up higher and higher. Okay? If you make this one up, this process is all of a sudden that is happening in a reasonable kinetics, and that's what is discussed in the kinetics. But by doing so, you are changing this K value. K value is a temperature dependent, and then I will show you the actual equation that we can do. But this is an exothermic reaction, and therefore is actually your K value is going to be smaller than 1 to million to 1 to 1,000. 1 to 1,000 is not so bad. So they are going to kind of balance the chemical equilibrium perspective with something that you will learn in the chapter 18, the kinetics, to find out what will be the nice balance. Because I don't want to do the reaction for a year to get 1 liter of products coming out. I want to do it in a reasonable time, so that therefore they are really changing. And the easiest one to change is pressure or temperature. Okay? And the most important one is actually temperature. So let's talk about the pressure. So 6B1. What about K versus pressure? Remember your Le Chatelier principle that you pressurize the system, the equilibrium shift to favor the reactant and the product depending on how much gas are being produced. But don't get be tricked by those Le Chatelier's principle of balancing the K value. They are just doing so that they can maintain the K value to be constant K. So why am I saying this? Is remember that delta Rg is 0 at equilibrium, and that's delta Rg standard plus RT ln K. So RT ln K, which is defined of K value, minus delta R G naught. So this K value, equilibrium constant, was defined, gives free energy change for the reaction at 1 bar condition. So it has nothing to do with the pressure changes. Once you have when you change the pressure, still the K is being defined by your state where the pressure is 1 bar. So value of delta R G naught independent of pressure. So therefore, your K value itself, or ln K value itself, is independent of pressure. So I guess there's nothing I can say more than just keeping you change the pressure, K value remain unchanged. Okay? And so that's what it is. But what about 2? K versus temperature. Okay. So can I change my temperature to change my K? The answer is yes. And we have talked about, we actually very similar form like this. So I think that what you really, I want you to develop some kind of eyes on looking at this. Yeah, K is changing, but actually what's really kind of changing is ln K is a form that is responding. When you change the temperature, it is actually 1 over temperature is you're changing it. And they are the proportion term. Okay? So this temperature change is equilibrium pressure change. But what is actually directly proportional is the natural log of equilibrium constant, their differences. Temperature differences is a 1 over temperature difference. So what's the meaningful is temperature is essentially thermodynamically meaningful in a way 1 over temperature. Okay? I think that you guys learned that, well, 25 degrees C, this is not thermodynamic description. You learn this is a thermodynamic description. Yeah, that's true. And this is a much better, and this is gotta be the one. But sometimes any kind of thermodynamic changes, it is actually the effective temperature is a 1 over K. Okay, 1 over temperature. This is a value that is actually the meaning of the temperature for what they have. I'm going to drive this equation, and so don't worry about that. Okay, so first thing is actually let's talk about our experience. Let's say exothermic reaction. Remember exothermic reaction, delta reaction H. This is positive or negative? Exothermic reaction? Negative, right? So this is a negative reaction. And exothermic is heat producing reaction. If you increase, when you increase the temperature, what happens when you increase the temperature? The heat producing the heat, you increase the temperature, they respond, they favor reactant, right? This is what probably, you remember the Satellite principle that you learned and put in a Chem 1. I think that this is probably the last portion of the exam. Probably probably the next exam is for them, this is about it. Okay, so, but now I have a much more exact and thus, favor the products and so on. So this temperature versus K is described by the equation called, it's also called the Vant equation. So for equilibrium constant. Remember we also talked about the Vant equation for the osmotic pressure. That was what was it? PV is mdRT. That was a Vant equation, right? And this is a different Vant equation. So he actually got a lot of meaningful, like what different kinds of property can be described. And this one is D ln K dt is RT squared delta R. So this is a Vant equation. And this was not, he didn't invent this equation from scratch. You already actually, if you're clever enough, actually, you can derive this equation from scratch to get this one. And probably you can put this as one of the equations that is not so different from the one. So the one that, when I look at this, there are two things that I want you to remember. One is, so this one, right? Delta R G naught is minus RT ln K. Everyone has no problem with this, right? So this is a what? These two terms that you wrote. So second one. Do you remember when you change the Gibbs free energy, let's say delta G over delta P over keeping temperature constant? Does anyone remember what this one was? Volume. So it was molar volume, and I think that you guys did all kinds of things, and we did it, right? But now the Gibbs-Helmholtz equation was, this, okay, so I want to know how the temperature changes. This is somehow related to do that. And this one, what about this? You guys remember it? Let me just put a Gn. Minus S. That's the first thing that you probably, but like I said before, this is a molar. This one is not so friendly thermodynamic quantity that you can easily measure. And then I remember the Gibbs-Helmholtz equation is, okay, instead of for you to looking at G responding to the temperature, how about G over T responding to the temperature? This is essentially a change of your thought. Okay? If I want to know the relationship between temperature and the G, instead of focusing on the G versus T, I can do G over T versus T. And all of a sudden, that the whole equation becomes very simple to do. And this Gibbs-Helmholtz equation, if you're looking at your note, G over T, T over P, all the mathematically it looks complicated. The answer is actually minus P squared H. So this is the equation. So instead of for you to dealing with the entropy Now G over T is something that I have to deal with an enthalpy. And enthalpy is something that I can easily measure. This is heat under constant pressure. So this is something that people love to deal with without dealing with entropy. And look at this. Looks like the G divided by T is related to ln K. So delta R G naught divided by RT is just minus ln K. Can you see that? Right? So this is a term that is actually G over T is the one that is actually quite responding to just behave like ln K. Right? We have this equation here, so all I need to do is just make a changes. Okay, let's put a delta here, reaction, and to that. That's all I did, changing from the Gibbs-Helmholtz equation just about the G versus H. Now delta G versus delta H for the reaction under standard condition. And then, well, I need to put R there, right? So I just need to put R there. And so all of a sudden that this term that you saw, delta G divided by RT, which is a minus ln K. Okay. You see the minus ln K on the other side? This one becomes minus ln K. Okay. And then you take the temperature derivative, and this one becomes minus RT squared delta R H naught. And then I will be happy to not dealing with double negative, so make it positive here. And then this is all of a sudden that this is a Vant equation. So the Vant equation that you see, which is I'm going to use this one to solve actual example problem, it is just an extension of what we learned from the definition of equilibrium